Hello everyone, I'm Shao-Yun Fang from National Taiwan University of Science and Technology, also known as Taiwan Tech. This talk introduces the advanced design methodologies for directed self-assembly. DSA is one of the next generation lithography technologies, which uses the self-assembly nature of a material called die-block copolymer to generate tiny layout features. Common copolymer arrange different monomers in a random way. In contrast, the two monomers of die-block copolymer are segregated into two blocks after an annealing process. The relative composition of die-block copolymers determines the preferred mode of assembly. As shown in this figure, when A-type monomers are much fewer than B-type monomers, the material forms a spherical morphology. With the increase of A-type monomers, the morphology transits from spheres to cylinders and then to lamellae. However, without additional forces, block copolymer can only form random patterns. For example, the shape of lamellae-type block copolymer will be like fingerprints if no additional force is made on it. To turn random patterns into highly oriented and aligned patterns, guiding templates are required. For example, if a guiding template is first used to generate this trench, cylindrical DSA can generate an aligned hole pattern, which becomes vias or contacts by removing the minority monomer and filling metal material. In addition, lamellar DSA can generate regular line space pattern with a similar process as shown in the figure. In cylindrical DSA, each via can be generated by using either a single hole template or a multi-hole template. However, since the overlay accuracy of the generated holes highly depends on the number of holes and the shape complexity of a template, only a few number of via patterns are regarded as manufacturable. For example, V4, V5, and V6 cannot be generated with a single multi-hole template because of its irregular shape. Different from cylindrical DSA, the process of using lamellar DSA to fabricate contact and via layer is more complex. Specifically, the self-aligned via process must be applied in combination with lamellar DSA. Here shows an example to generate a via connecting an M1 wire and an M2 wire. After the M1 wire is done and the trench of the M2 wire is made, a guiding template is formed. By filling BCP material, removing the minority monomer, you can see that the trench of the via can be produced at the intersection of the M2 trench and the template trench. And finally, the metal material can be filled into the via trench and the M2 trench simultaneously to get the result in the last figure. Although DSA can be used to generate tiny holes or a thin and dense line, guiding templates are generated by using conventional optical lithography. Since the resolution of conventional lithography is quite limited, given an arbitrary layout, it is hard to legally perform template assignment for every via hole by only using one single mask. Therefore, using multiple pattern lithography for guiding template generation is an intuitive and effective way. Multiple patterning uses multiple masks for the lithography process for every single circuit layer layout. In the example shown here, the four dense trenches can be produced by using two masks, and the pattern pitches on each mask can be greatly relaxed compared to the pitches of these four trenches. There have been a few existing studies considering via fabrication with cylindrical DSA, which can roughly be categorized into three types. The first one is to perform simultaneous guiding template design for DSA and guiding template mask assignment for multiple patterning. The second group of papers additionally consider the design constraint induced by using multiple BCP materials. And finally, some DSA-aware detailed routing strategies have also been proposed. Due to this spatial hybrid lithography technology, that is, we use multiple patterning for guiding template generation, and then use DSA for contact or via hole generation. There are some emerging design challenges. The first one is to perform simultaneous guiding template design for DSA and template assignment for multiple patterning. Here shows an example of 5 vias. An arrow indicates that the 2 vias cannot be fabricated with conventional lithography on the same mask. In DSA, we usually need to first identify which vias can be feasibly grouped and whose grouping can lead to better via manufacturability. That is, we need to find which vias should be grouped to minimize the number of conflicts. On the other hand, if we adopt multiple patterning for these 5 vias, then we need to determine which mask should be used to generate each via. By transforming this into a graph coloring problem, we need to determine the color of each via such that 2 conflicting vias can have different colors. So in the hybrid lithography consisting DSA and multiple patterning lithography, we need to determine which vias should be grouped, and so vias in the same group can be assigned the same color. And also, we need to color the rest of vias to generate a conflict-free result. By comparing the coloring solution derived from this multiple patterning lithography and that from the DSA multiple patterning hybrid lithography, we can observe that the advantage is that for the same via layout, fewer masks are required by this hybrid lithography. For such an optimization problem, a previous work proposed an approach to deal with the contact layer of standard cell-based layout. Since the layout of each standard cell is fixed, it is possible to first enumerate all the coloring solutions of each cell by considering DSA grouping and coloring. And for each pair of adjacent cells, if a coloring solution of the left cell and that of the right cell is originally compatible or compatible by considering DSA grouping, such as the 2 examples shown here, an edge will be added between the vertex representing the 2 coloring solution. So for a row of cells, a solution graph can be constructed as an example here, and the feasible solution exists for this cell row if a path can be found from the source node to the target node. However, a general via layout does not have such a good property of row-based and fixed contact layout of cells. So algorithms tackling this optimization problem for general via layouts are also proposed. Basically, these works usually rely on this kind of via conflict graph, where a spacing edge exists when the distance between 2 contacts is less than the minimum spacing rule on the same mask. And the grouping edge exists when 2 neighboring contacts can be grouped. One of the 2 existing research works listed here propose an LP formulation and a heuristic algorithm, and the other one proposed a graph-based algorithm that can simultaneously minimize the number of conflicts and the total template cost. The above 3 works adopt a single BCP material whose hole pitch is equivalent to routing pitch, and so only straight templates can be used. In addition, since in cylindrical DSA, The overlay area of generated hulls highly depends on the size and the shape complexity of templates. Only these three kinds of templates are considered as feasible, which may not be sufficient. For example, here shows a via conflict graph composed of four vias, which have spacing edges with each other. Since the distance between the upper two vias are larger than a wire pitch, they cannot be grouped. And as a result, there will be an inevitable conflict if only two masks are available for template generation. To enhance the design flexibility of templates, the following works consider to adopt two different BCP materials. The first BCP material is chosen, whose nature pitch is equal to the wire pitch, such that these straight templates can be used. And then the second BCP material is chosen, whose nature pitch is equal to the distance between two vias at the two diagonal corners of a grid. That is, its nature pitch equals square root of 2 times the y pitch, such that these slanting templates are also feasible. And so for the previous example via layout, by using a straight two-hole template and a slanting two-hole template, we can easily generate these four vias without conflict. However, the adoption of two BCP materials also induced new design constraints. Since each lithography step can only use one BCP material, the templates generated by the same mask need to have the same via pitch. So if the first mask uses the first BCP material, it cannot generate slanting templates. And if the mask using the second BCP material, then it cannot generate these straight templates. This ASCII work proposed an LP formulation and a heuristic to solve the template design and mask assignment problem by considering the flexibility and the constraint induced by using two BCP materials. Another work also considered using two DSM materials for a via layout. While they consider each BCP can have a feasible pitch range. And this assumption makes mask assignment more flexible and may result in larger solution space, and so solution quality may be improved. They also consider the mask assignment constraint induced by the different BCP types. In this work, a DSA pitch range optimization method is first proposed with multiple variable regression model to minimize DSA decomposition conflicts. After that, the double BCP decomposition problem is formulated as a maximum weighting independent set problem, and then efficiently solved by using a bounded approximation algorithm. There is also a state-of-the-art work on the same optimization problem, which adopts one more 2D template to enlarge solution space and so improve solution quality. In addition, this work proposed a new graph model with spacing edge and template hyperedges and reduced the template assignment problem to an exact cover problem. In this way, a concise LP formulation and a fast backtracing heuristic are then proposed to achieve great runtime improvement. Considering semiconductor manufacturing, cylindrical DSA suffers from some disadvantages. First, the via displacement error increases with the number of holes and the shape complexity of a template. Second, the multiple vias generated in a single template are evenly distributed, and so the spacing between each pair of vias in a template have to be identical. And these two problems can be overcome by adopting lamellar DSA with the self-aligned via process. in which via holes are produced at the intersection of the vertical metal wires and the horizontal guiding templates. And therefore, the produced vias are immune to displacement errors caused by the imperfect aspect ratio and dimensions of templates. In addition, lamellar template can produce multiple via holes with different via pitches, increasing the flexibility of template design. So as a result, an example layout shown here shows that lamellar DSA may resolve more conflicts compared to cylindrical DSA. There is one existing work that proposes the corresponding template design approach in the post-layout stage. The design constraints induced by the process of lamellar DSA with SAV process are first identified. First, a template cannot cross over a vertical metal wire where no via exists at the intersection. As shown in this figure, if vias V1, V2, V3 are grouped into a template, and an expected via will be generated at the location indicated by this cross, resulting in a circuit short problem. Second, a template should not be too short to guarantee acceptable edge placement error. A template that is shorter than 2.5 routing pitches is regarded as a short template, and the number of short templates should be minimized for yield optimization. So as shown in this right figure, the template for V1 is extended to avoid being a short template. In this work, an ILP-based approach and a heuristic method are respectively proposed to solve the template design and mask assignment problem for lamellar DSA. In conclusion, this presentation introduced DSA as an advanced lithography technologies. The difference in the process and thus the design constraints between cylindrical DSA and lamellar DSA are differentiated, and the existing studies on the two technologies are briefly introduced. To facilitate DSA compliant layout synthesis, design methodologies or even design rules are required to be further developed. And for lamellar DSA, multi-row templates can also be adopted to further enhance the design flexibility of guiding templates, which can serve as the future research directions. Thank you so much.